Now we have started from here. One loop is there in the magnetic field, and when the magnetic field starts changing with time, then we have observed that EMF is induced. Deflection has shown with the galvanometer. Now we have reasoned that cos is the induced electric field. Due to the time varying nature of magnetic field, an electric field has been induced. This is something different from the electrostatic field. Those all points we have seen. Now from the Faraday law of electromagnetic induction, EMF induced is minus d phi by dt. But here in this region, actually induced electric field has been developed. So this induced electric field, just like dV equal to minus E dot dr, even though this is non-conservative field, induced electric field, a potential difference has been developed because of this between any 2 points. So along this conducting circular loop, the EMF induced in terms of this induced electric field will be E in dot dl, or you can say dr, whatever you want to write. Just like dV equal to minus E dot dr, that type of expression, even though this we have to call the EMF and not the potential difference. So by using this equation, we can find what is the value of induced electric field. Once again telling, because of the time varying nature of the magnetic field, induced electric field has been developed in this region. Because of that induced electric field between 2 points, an EMF has been developed between these 2 points, which is given by E induced dot dr. Right? Now this is about the induced electric field and the flux relation. Now come back to the something more critical. Consider one situation and see what will be the expression of the induced field. Let us consider one cylindrical region. This is one cylindrical region in which uniform magnetic field is present. In which uniform magnetic field is present. Field is into the board, and in this entire region, this boundary, the field is there in this way, like a cylindrical region. Now this magnetic field is increasing with time at rate dV by dt. Means magnetic field is increasing into the board. Magnetic field is into the board and it is increasing with time. Our task is to find induced electric field expression for, let us say, this cylindrical region is of radius capital R. For inside point and outside point. We want to find the electric field here also and here also. This is our task. Now, to find this particular thing, what we are doing, for inside point, I am taking this loop. Now magnetic field is varying with time, so a induced electric field has been developed. Now to find the induced electric field at a distance r, I have considered a circular loop of radius r whose center is coinciding with the axis of the cylindrical region. Now due to the symmetricity of this arrangement, we can say induced electric field will be along the tangent to this. It can be along this side or this side. We are going to decide which way it will come. Let us say, without mentioning the direction for the time being, I am writing induced electric field is E for R less than R. Now what is the flux linked with it? B into pi R square. This is the magnetic flux linked. Then what is the d phi by dt? D phi by dt is equal to dB by dt into pi R square. Now negative sign will come in the EMF, but we will find the sign of the induced electric field by using the Lenz's law. That's why I won't write in the next line EMF equal to minus d phi by dt. I'll simply write d phi by dt only. So now what is going to happen? If I find closed integral of E dot dl over this loop, electric field is along the tangential direction and angle between dl vector and E vector is 0, so it will come E into 2 pi R. Now from the expression E dot dl equal to minus d phi by dt. Minus sign is going to tell you only about the direction of E. What about direction? Because there are two possibilities. So this minus sign I am dropping. So we will have E into 2 pi R equal to dB by dt into pi R square. Pi R cancel. So EMF you got, induced field into dB by dt. This is the induced electric field for inside point. Magnitude comes. Now the task left only about the direction. How to find the direction, whether this way or this way. Now for that we will use the Lenz's law. This original field into the board and increasing. So the field due to E induced has to be outward. Now, how the induced field will cause the magnetic field? Magnetic field due to the induced electric field. Now, if some charge particle will be here, under the action of this induced field, this charge particle will move. Let us say this charge particle is positive. Under the action of this induced, if the field is in this direction, this is the direction of force. If the field is in this direction opposite, this is the direction of force. If field is in this direction, it will move in this way. So the charge particle will move in the direction of induced field. It means current is in the direction of induced field. Now it means the magnetic field due to induced field has to be outward. Magnetic field due to current due to induced electric field has to be outward. So in place of current, your direction comes of this one, because direction of current and direction of induced electric field will be same. Charge will move in the direction of induced electric field. Charge will move in the direction of electric field means current is also in the direction of induced electric field. So if induced electric field this way, then magnetic field due to the induced current will be into the board, which is not according to our situation. So here in this particular case, induced electric field has to be in this way. So for this situation, the induced electric field direction will be this one. We can say anti-clockwise, right? So have a look, note it down, devote 2 minutes to absorb it. After that, continue with the next part. So here, for the inside point, we have found the induced electric field expression as R by 2 dV by dt. If the field is increasing into the board, then the direction of this field comes out to be in the anti-clockwise direction. Now we are doing the same thing for outside point. Now we are interested in finding the induced field for outside point. Now for outside point also, we will take this one. This is the inside point, this is outside point. Now for R greater than capital R for outside point. Let us say induced field is E, then E dot dl over this path will be this. But now for this circular path, field is present only for capital R. Field is present only in this region, right? In this region there is no magnetic field. So the flux linked with it will be pi r square, not small r, it will be only capital R. So it will become dV by dt into pi r square E into 2 pi r. So r square upon 2r into dV by dt. This is the field at outside point. So if I draw the graph for the field versus r, for inside point it is r by 2 dV by dt, and for outside point r square dV by dt upon 2r. It is linear function and here it is capital R, right? This is about the induced field EMF and induced electric field. Now you see one very important thing. Is there any magnetic field present here? No, magnetic field is present only up to here. In this region, no magnetic field, but still induced field is there. Still induced electric field is there. What is the cause of the induced electric field? Time varying nature of the magnetic field. But in this you see the induced electric field develop even at that point where no magnetic field is present. A very important thing, very important point, because sometimes students get confused in this small part also. So one important point about the induced electric field you can write. Induced electric field can be present even if at a point, even if no magnetic field is present at that point. Right? Now, the most important point of the induced electric field. In the first part, I have drawn this diagram. This is kept in a magnetic field and this is a conducting ring attached with a galvanometer, kept in uniform time varying magnetic field. Now if I say this ring is of non-conducting, it is of insulating material, remaining all situation remains same. It is of non-conducting material, non-conducting ring. Will the EMF appear? Will the current flows? Now, if it will be the case of motional EMF, then it is no EMF, no current. But here, in this case, if it is of non-conducting, induced EMF will develop. Existence of induced electric field is independent of the presence or absence of any material. I am writing this statement on the board. You copy it. I am sure you will understand. Existence of induced electric field in a region is independent of presence or absence of any material. Forget the conducting or non-conducting. I am saying any material, whether the material is present or not, then also the induced electric field will be there, provided time varying nature of magnetic field is there. Existence of induced electric field in a region is independent of the presence or absence of any material. It solely depends upon the time varying nature of magnetic field. The presence of conducting ring or conducting material. In the first part, we have taken the conducting ring attached with the galvanometer. Why then? The presence of conducting ring or material is only facilitating us to check the existence of induced electric field. Write it down. I am explaining this point in depth. Now, let us consider in this region, in this cylindrical region, magnetic field is varying with time. Nothing else is present in the region. No material. It may be vacuum. It may be any insulating material present or not. It may be any conducting material present or not. Right? That type of situation. Here nothing is present. Only thing, magnetic field is going into the board and it is varying with time. Then here, at different points, induced electric field will be there. Right? Where the material is there or not doesn't matter. Induced electric field will be there. And if induced electric field is there between these 2 points, EMF can also be there. Then why we need that conducting ring? With the help of this conducting ring, we identified, we checked, we confirmed that some current is there. Some current is there, some induced EMF is there. So this is only a means, only a way to identify that induced electric field is there. Right? This is all about the induced field EMF. Now 1-2 questions I want to discuss. I am discussing that. From SC Verma, only 2 questions are there on this particular topic in the exercise 64 and 65. You can do it easily. Try to complete it. So from SCV, question number 64, 65 you have to do. Now I am taking one question. Not 1, 2, 3 questions I will take. This one is nice one. A uniform magnetic field B exists in a cylindrical region of radius capital R. One cylindrical region is there, here uniform magnetic field B naught is existing. Conducting ring of radius A greater than R. A greater than R. So here one conducting ring is there. This one, its radius is A, which is greater than R. And this is conducting ring. And they have said, is placed coaxially with the field region. Ring has mass m, linear charge density lambda. Mass m, linear charge density lambda. Angular velocity gained by the ring if the field is switched off. They are saying, what is the angular velocity gained by this ring? This ring is going to gain some angular velocity. Find the angular velocity of this ring if this magnetic field is switched off. If the magnetic field is switched off. So actually the magnetic field is becoming B naught to 0, means it is varying with time. Switched off, same time dt. Say magnetic field is changing with rate dV by dt. So it is the outside point of this magnetic field region. So if we want to write the value of the induced electric field, E into 2 pi A equal to dV by dt into pi r square. Magnetic field is present only in this region. This will come. So here you will get E is equal to dV by dt into r square by 2A. Now because of this E, induced electric field, now field is decreasing. Field is becoming 0 from non-zero value. So field is decreasing, so the induced electric field will be this direction. So the direction of induced electric field will be this way. Now this conducting ring is having the charge density lambda. So if I consider this small part of charge dq, it will experience the force dqe. Here also it will experience the force dqe. Here also dqe. And this force will cause the torque here. Understood? Electric field is same everywhere. So the total torque will come out to be Q, lambda into 2 pi A into E. This is the total torque. Now magnetic field is changing in 0 time. So the induced electric field, this dt is very small. So this induced electric field is impulsive. So this torque is also impulsive. So what is the angular impulse? Is equal to lambda into 2 pi A into E dt. And if I take this dt this side, E dt is equal to dv into r square by 2a. Integral, this is B only. So angular impulse is equal to lambda into 2 by A into E dt comes B into R square by 2A. Right? Now minus sign etc. I have dropped because direction I have written directly without using the minus sign. So here angular impulse we know from the rotational motion equal to final angular momentum minus initial angular momentum. So L final minus L initial 0. L final is I omega. I value will be mass given m into a square. I is m a square omega. So your omega comes out to be lambda into 2 by a into b r square upon 2a into m a square equal to omega. This is your angular velocity, right? Very nice question. Combination of the impulse, angular impulse, rotational motion, EMI, induced field EMF, everything has been involved, and one of the nice question I will say. One more question we'll try. This becomes little difficult question in the first phase. But actually on this topic, most of the questions are nice only. This topic itself is very nice. One more question I'll take. Let us consider a cylindrical region. Cylindrical region in which uniform magnetic field is there, which is increasing at constant rate alpha Tesla per second. dV by dt is alpha Tesla per second. And the radius of this cylindrical region is r. And there are 2 points marked, say A and B, at a distance of r. So at a distance of small r here, these 2 points A and B are marked. We want to find the EMF induced across AB. We want to find the EMF induced across AB. This is what we have to find. So again the same thing. Say my circle has not become good. Like this. Say this distance is x. This distance is x. This one. Right? So at a distance of x, what is the induced electric field? E equal to x by 2 into dV by dt. And direction? Because this field is increasing, so induced field has to try to decrease it. So direction will be anti-clockwise, this way. Right? Now, if this is x, electric field here is this value, x by 2 into alpha. Say this angle is theta. This angle is theta. And I am taking at a distance of y this dy. I am moving that side. So E dot dy, dE equal to E dot dy. What is the angle between this E and this dy? Theta only. So it will become E cos theta into dy. Right? Now E is equal to x by 2 into alpha. E is equal to x by 2 into alpha. Cos theta is base upon hypotenuse, that is r by x. R by x, and into dy. This will come. X cancelled. So it becomes alpha r by 2 into dy. In this alpha constant, 2 constant, r constant. Variable left only dy. So the total EMF generated is y varies from minus of this to this distance. Now this is given as r. This is small r. So what will be this distance? Under root r square minus r square to under root r square minus r square. So it will become alpha r by 2 under root r square minus r square. This is the answer, the potential difference between these 2 points. I hope you have understood. You have some holidays. I will suggest see this video properly, make the notes. If any doubts will be there, we can discuss it in the class, right? So we are stopping here only, and those 2 questions from S.C. Verma also you can solve them. Okay, good day.